The fundamental theorem of calculus part 2. Actually, you already know the fundamental theorem of calculus part 2. But before we get into it, I want to look at some examples of something we've done in the past, but we're going to change the way it looks. And the way this looks is very important, okay? If I give you a derivative function, whatever it is, if I give you velocity, what is the antiderivative representing? In a sense, the position, yeah, okay? So let's see here. Oh, I gave it away. What do you have to include when determining an indefinite integral? Let me take a step back. What is an indefinite integral? Because what have we been doing all along here? We've said the integral from 3 to 7 of whatever, f of x dx, what is that called? This is a definite integral. Okay? And what kind of answer do I get for an indefinite or for a definite integral? I get a number. And what concept am I dealing with when I'm taking an integral? I get a number, but what am I finding? I'm finding an area somehow, right? Area under the curve. If I want an indefinite integral, what's the difference between indefinite and definite? You've seen it on Khan Academy. There's no what? There's no limits, right? So there's nothing to plug into. We can't find a numeric value. We can't find an area under the curve. What does this mean? What's another way of saying the integral of a function? What? Antiderivative. That's all this is. This is an antiderivative. Now, what kind of answer do I get for just taking an antiderivative? I get a function, right? I get some sort of function. And when I take the antiderivative, you just saw it a second ago, what do you have to make sure you plug in? The plus c. Why did I not have to put the plus c on the definite integral? There it is. When I go to take the antiderivative and then subtract the upper and lower bound thing, right? The c's cancel out, right? So in this case, the definite integral, we don't need the plus c. But in an indefinite integral, which is just an antiderivative, you need to have the plus c because we're getting a function. Now the question then becomes, what does the plus c mean? What does it mean? Kind of where it starts. It's plus a constant. Okay. So if I was going to check my work, right, if I take the antiderivative and then I get an answer, what am I going to do to make sure I'm right? Take the derivative. So when I take the derivative of plus c, what do I get? 0, so that's why it's not there. In other words, how many functions are antiderivatives to a function? Many? Lots? Because c is any constant, right? What does it represent on the graph? Like a y value. The plus c represents what in a graph? A y-intercept maybe, right? If I just add a constant number to any function, what happens to the graph? It shifts up or down depending on that value, right? So that's all c is on a graph. It's the vertical shift, up or down. Okay, so let's take a look at an example of this. Okay, normally we start out at 0. That's assuming c is 0. You guys figure this out. What's the integral of 3x squared minus 4? All right, so what does this mean, the integral of 3x squared minus 4 dx? What am I asking you to find? The antiderivative. So what's the antiderivative of 3x squared minus 4? X cubed minus 4x plus c, right? And again, that c represents the vertical shift. So if I'm looking at the graph, what does this graph look like? It's polynomial with 2 bumps. Why? Why is it 2 bumps? Think calculus. True, it's less than 1, but why is it less than 1? Because when I take the derivative, the power does what? Decreases by 1, which means it changes directions twice, right? So that's calculus. Where does it change concavity? How many times does it change concavity? Concavity deals with what? Once. Why? Because we're going, what does it look like? It's going to look something like this, right? So here, right there is where it changes concavity, right? Okay. And the reason that's the case is because What changes concavity? What causes concavity to change? When the what?
When f prime is changes from
When the second derivative changes signs. Okay. When the second derivative changes signs. So that is when c is 0. C could be anything, though. C could be up 4, positive 4, or C could be negative 4, or anything else. So when I take an antiderivative, what I'm actually doing is finding a parent function of all the possible functions that are antiderivatives. Okay? What is it you need to find C? A point? What did I call that point a while ago? There's a word for it. No? I has something to do with it. Oh, because you have. The initial condition. Do you remember that? All right. So, let's look at an example, okay? dy dx equals cosine of x if the graph of y passes through the point pi 5. What is y? We'll do this one together. dy dx equals cosine of x. I'm asking for y. What's another way of saying dy dx? Y prime, right? Now, this is the normal way about going about things. I'm going to rewrite this as y prime equals cosine of x. How do I find y? So y equals sine of x plus c. Okay? How do I find c? Plug in the, what's it called? Initial condition, so what's y? 5 equals sine of pi plus c. Sine of pi is sine of pi, 0, so that's just c. So our final answer is y equals sine of x plus 5. Right? Easy, right? Okay, so I'm not trying to trick you today, but we do have to note that there's a different way to write this. Okay? This is called the traditional form. So you just take the antiderivative. So the notation would be the integral of cosine of x dx. When I do that, I get plus c, and then I plug in my initial condition to find out what c is, and then rewrite the function. But what was a requirement for me to be able to do all that work? The point, yes. Yeah, that's the initial condition. The plus c, all that. But what must I have known in order to actually figure out the final answer? I needed to be able to take the antiderivative. Now, I told you before, you can take every derivative there is known to man. But you don't know how to take every integral, and nobody does know how to take every integral. There's rules that help you in a lot of them, but not every one of them. So the question is, what does this look like if I can't take the antiderivative? Okay? So what we're going to do is what's called the integral form. So this is only if we're capable of taking the antiderivative. So the integral form is going to look different. Okay? Now I want to explore this for a minute. Let's think in terms of definite integrals. Again, if this, let's say I've got the integral from 5 to 9 of cosine of x dx. Right? Can you do that? Can you solve that? Can you?
Yeah.
You can, right? You would take the antiderivative and then plug in the upper and lower bound and subtract, right? What kind of answer do I get? A number, right? I get a numeric value. But what is the answer supposed to be here? It's supposed to be a function. So here's what I'm going to do. If I put x here, oops, what is the variable of this expression here? X. Remember, the t and the dt are just placeholders. The real variable is in the integral. You get what I'm saying? Am I going to get a numeric value here? No, because x has a variable. Get what I'm saying? Now, let's see what we get here. What if I were to say the integral from pi to pi of cosine of t dt? What do you know that is? That's a 0 value. But wait a minute. Back in our problem, it said that this curve, whatever it is, passes through pi comma 5. What does this thing pass through? Pi comma 0. Let's say this. Let's say I've got the integral from pi to x of cosine of t dt. Let's say that is my equation. Okay? The lower bound is pi, the upper bound is x. Okay? If I say the initial condition is pi comma something, when I plug pi into x, what kind of answer am I going to get? 0. You guys okay with that? Did I want that? No. I want the answer to be 5. So what is the difference between the integral, what is the difference between plugging pi in here? Because how do I find the y value when I'm dealing with any function? Just plug in the x value, right? So if I plug in the x value, I get pi to pi of cosine of t dt. So that's not what I want. That's 0. So how do I get 5 out of it? What do I have to do to get 5? What do you say? I have to do a vertical shift. How do I do that? Plus c. But we know what it should be kind of now. What do I have to add to this to get an answer of pi comma 5? You guys see that? Okay. Just try and wrap your head around that, okay? The integral form, and again, I just said the integral from pi to pi of cosine of t dt is 0, but I'm going to write this like this. The integral from pi to x of cosine of t dt. Notice what's happening here. The variable, is the upper limit, right? Where did this pi come from? Why did I choose to put pi there? Because that is the initial condition, right? What's an initial condition? It's where everything starts, right? So the lower bound is where everything starts. So our initial condition is pi, or the x value of the initial condition is pi. Our variable is x, and then this is what we're taking the antiderivative of. Does that make sense? But this does not produce pi comma 5. It produces pi comma 0. So what do I have to do? Plus 5. So this is the integral form. Write that down if you haven't written that down. Okay. Let's see what I have. You guys okay with that? Mm-hmm. It can get a little confusing, but again, the key to this, it doesn't matter how we solve this, or it doesn't matter if we can solve this. We can. In fact, I probably should. If I say y equals the integral from pi to x of cosine of t dt plus 5, let's do this. What's the antiderivative of cosine? So sine of t evaluated from pi to x, and then plus 5 when I'm done. So what do I get? Sine of x minus sine of pi plus 5. So y equals this, y equals that. Y equals then sine of x. That's 0, so just plus 5. And that's exactly what we had before, right? So this is just another way of writing the function. It's the integral form. Just like on a line you have slope-intercept form, you have point-slope form, and you have all those different forms, right? This is just another way of writing antiderivative of some sort, okay? The key is, why is this way important? It's for functions that I don't know the antiderivative of. Okay? Yeah? Okay. All right, try this. Let's look at number 1. Okay? If dy dx equals 1 over x, we ask ourselves, do we know the antiderivative in order to get y? Yes, we do. So we'd say y equals natural log of x plus c. Now, we'll get into why this is true later, and maybe you can understand why right now, but we're going to put absolute values around that x. Why? Because the natural log of a negative number does not exist, right? E raised to any number will never be negative. So we put absolute values. It's not a big deal for right now, but we'll get to that later. So we say 4 equals the natural log of 1 plus c. What's the natural log of 1? 0. So c equals 4. So our answer is y equals the natural log of the absolute value of x plus 4. That's the traditional form, yeah? What's the integral form? It would be y equals the integral from 1, because 1 is the lower bound, right? This is the initial condition, to x of 1 over t dt. Now that is the integral from 1 to x. If x is 1, what is this going to produce? 0. I don't want it to produce 0. I want it to produce 4. So we're going to say 4 plus. Now on my other examples, I put the 4 afterwards, but this is the way you normally write it. You guys okay with that? Okay, and we can go through and verify it, but try and understand what's going on here. What's the process in evaluating this? Take the antiderivative. That's what I did here, right? And then when I plug in these points, I'm plugging in x and 1. There I'm plugging in the 1, and I'm figuring it out. So it's basically the same process, but it's just a different way of writing it. Are we okay with that? Sure. Yeah. Don't sound so excited. Now, why is this not x? Because that's the variable, right? And this is just taking its place for right now until we deal with it later. Okay. What did you guys get for the second one? What do you got? Nothing? Do you know the antiderivative of secant? No. You do know the antiderivative of secant squared. What's the antiderivative of secant squared? Tangent. But we don't know the antiderivative of secant. So we can only write this in integral form. What would it be? Okay. So y equals the integral from -4 to x secant t dt plus 7. The lower bound is the initial condition's x value. The upper bound is your variable. We get rid of the variable in the secant function, or in the integrand, and replace it with dummy variables. And then we put plus c at the end because we want the final answer to be 7 when I plug in. I put in plus 7 because we want the final answer to be 7 when we plug in -4. We good?
Wait, so that's the answer?
That's the answer. There's nothing more you can do with this because you don't know the antiderivative of secant. What about the last one? Do you know the antiderivative of that guy? No? So somebody else besides Miguel. Y equals. You'll start it off, right? Thanks for starting it, Jenny. Okay, the integral from 6 to x sine squared rad t plus 4 dt minus 3. Okay. Okay, the fundamental theorem of calculus part 2. How exciting. Now that was just rewriting equations. That was just changing forms. All right, are you ready for this one? Are you excited? Yes? Yes? Here's what it says. It says, if a function, if f is continuous over a closed interval a to b, then the integral of f of x dx from a to b is capital F of b minus capital F of a, where capital F is the antiderivative of f. Do you agree with that? That's something you already know, right? That's the fundamental theorem of calculus part 2. That's it.
Woo! That's so cool.
See, it wasn't that you were excited about learning something. You were excited that you didn't have to learn anything new. Oh, jeez.
Well, I mean, we already learned it. We're just like
All right.
As if you didn't know.
it again.
So the fundamental theorem of calculus part 1 says basically what from yesterday? The derivative and the integral basically cancel each other out. You just have to make sure you use the chain rule, right? Okay? So basically the derivative of the integral is the integrand, right? With the exception of the limits being a function, okay? The fundamental theorem of calculus part 2 says if you want the integral, then all you have to do is take the antiderivative, plug in the upper bound and lower bound, and subtract. Or if you want the definite integral. Yeah?
Yeah.
Okay, let's look at a problem.
Mr. Monday. We already knew
It's
that.
so important, I had to say it again.
Repeat it. Repeat it. Correction.
All right,
Minus 1 point.
let's do this one real fast. The integral from 0 to 1 of x squared plus rad x dx, I can guarantee you I can guarantee you some of you are thinking, whatever, that they know what they're doing, but they're going to make a mistake. What do I have to do? Antiderivative. Okay, this one's easy. 1/3 x cubed plus, I know that one. I got that memorized. 1 over 2 rad x. The derivative of this is this, yeah? So now you see it's like, okay, calculus gets hard when you have to take the antiderivative and the derivative and everything else because you're accidentally going to take the derivative when you should have taken the antiderivative, and you're going to accidentally take the antiderivative when you should have taken the derivative. Right? So let's rewrite this. 0 to 1 of x squared plus, that was the derivative, but how did I figure out what that was before I had it memorized? I rewrote it as an exponent, right? So it'd be plus x to the 1/2. All right, now let's take the antiderivative. What's the antiderivative of x squared? 1/3 x cubed plus, this is going to be x to the 3/2, and then 2/3 out front. And then that is all evaluated from 0 to 1. You guys okay with that? Be very, very careful. Almost felt like Elmer Fudd. Be very quiet. I'm hunting webbing.
Please don't cut that out.
Okay, so that's the first one. I'm going to plug in the upper bound. Minus 1/3 0 cubed plus 2/3 0 to the 3/2. Okay, so this is 1/3 plus 2/3 minus 0, so 1. Right? It's good practice. That's it. You knew you were going to get a numeric value because the limits were both numbers, right? Okay. You guys got that?
Yeah.
I've got that. Just make sure you don't take the derivative when you're supposed to take the integral. All right, number 1. First of all, what is the antiderivative? X to the first is x to the what? Negative 1/5, because we have to add 1. So what's the coefficient going to be out front? Negative 5. Okay, evaluated from 1 to 32. So it's going to be negative 5 times 32 to the negative 1/5 minus negative 5 times 1 to the negative 1/5. Well, this one's easy enough. This will be plus 5, right? This one is negative 5 over 32 to the 1/5. So what is that? That's negative 5 over 2, 4, 8, 16, 32, 2. Plus 5. So negative 2.5, so 2.5, so 5/2, yeah?
Yeah.
5/2? Okay. What about number 2? This is an important one, because this gets you. All right. Do we have an answer? Natural log? You said natural log? The antiderivative is natural log? No. Be careful on this, okay? And I think I've said this in the past. What students tend to do with problems like number 2 with 2 over x squared, they see something over x and they automatically think natural log. That is only true if it's 1 over x or something over x to the what? What is the power for natural log? Yeah, only when the bottom has a power of 1. Then you could get natural log out of it. If it's any other power, what do you have to do? You have to move it to a negative exponent and then take the antiderivative. So what's the antiderivative of 2x to the negative 2 then? X to the negative 1. What is it, negative 2? So negative 2x to the negative 1. Stop it. So that would be negative 2 over x evaluated from negative 2 to negative 1. So negative 2 over negative 1 minus negative 2 over negative 2, which is 2 minus 1. 1. All right, so these other ones were pi 2 rad 3 and 0.